Okay, deriving trig functions, yay! Okay, before you all mutiny, 9I, j and k is what I'm going to set. However, j and k you've already done half of it. It's just the trig stuff that's in j and k. It's got a mix of e's and logs and stuff like that there. So it's nowhere near as long as it first seems. Okay, cool. Written out 3 sets of rules that are the general. We'll go back to those instead though. So there's a whole bunch of different ways to show it, but I'll probably just link to stuff on YouTube for that, or you're welcome to search it up yourself. Turns out that when you derive sine, you get cos. When you derive cos, you get negative sine. And since you already know the derivative of sine, that's cos, well the derivative of negative sine must be negative cos. Since you already know cos goes to negative sine, the derivative of negative cos must be negative negative sine, or in other words, positive sine. So I'm just going to write negative sine here. Cool, well that's actually the same as this guy, so the derivative of this goes back to here. And so the derivative of that, and then you just go on forever, indefinitely. Cool, so trig functions, infinitely derivable, which is a cool little thing given that they go around in circles originally to define them, and now they go around in circles when you derive them as well. Cool, okay, so let's throw in a little more complication. If you've got a scalar, as always with your derivatives, the scalar is just going to stick around in your derivative. The only extra annoying thing, so sine goes to, whoops, good job, I wrote sine instead of cos there. There we go, fixed. So sine will go to cos. The only extra bit is if you've got a function in here, you've got chain rule operating as well, so derivative of the inside comes out and the original inside just stays. Similar story with cos, cos goes to negative sine. You've got your scalar and you've got a chain rule going, so derivative of the inside and the original inside. More problematic is tan, because it doesn't turn up anywhere in this nice cycle. So we've got this thing going on. Tan we can think of as sine over cos, which I'm going to treat sine as u, cos as v, and we're going to run quotient rule on it. So u prime is cos, v prime is negative sine. There's our nice quotient rule. So subbing everything in, we get cos by cos minus sine by negative sine all over cos squared. Great, well, negative sine times negative sine becomes positive sine, so this is cos squared plus sine squared. Cos squared plus sine squared, hang on, that's 1. We know that from the other identities. So that's 1 over cos squared, great. There's conventions, this squared you can write as cos squared of x rather than cos of x all squared, just to save a little bit of extra bracketing, which can lead you into a bit of trouble because you miss one and then all of a sudden everything falls apart. So we've got 1 over cos squared. More things for you if you haven't seen them already. 1 over cos is sec, and so 1 over cos squared is sec squared. If you're not familiar with these already, 1 over sine squared, so the inverse of sine, is, sorry, the reciprocal of sine, I should say, is cosecant of x, which is shortened to CSC of x. 1 over cos is secant, which is shortened to SEC, and 1 over tan is cotangent, which is shortened to COT. So I'll say cosec, sec, and cot, just to say them faster if I have to say them. But if for methods, generally they don't come up that much, with the exception of sec, simply because when you derive tan, it'll turn up. Also, you should probably be aware of them, or at the very least have them in your bound reference, because it's possible that you fiddle around on the CAS in the middle of an exam and it will try to help you by throwing it into one of these versions. So you have to be able to read it, otherwise you're going to be really upset. Okay, so we've got a couple of examples to go. These are all my original functions. Okay, sine of 3x, great. Well, I've got a function inside a function, so I can just run this rule straight out of the gate. Derivative of the inside, 3, derivative of the outside, cos, original inside, done. Nice and boring. Okay. And I'll put f prime x equals, cool, f prime of x for the next one. Cool, alright, similar story, I've got a derivative of the inside first, so derivative inside to x, derivative of the outside is negative sine of the original inside. Beautiful, boring. This guy, okay, well, tan's a bit more complicated, goes to sec squared. Okay, derivative of the derivative of the inside, okay, well that's 3x squared. Great, derivative of the outside is sec squared. original inside, x cubed minus 8, and that's it. That's it, yep. Cool. So they're all pretty straightforward when you're just following the rules. Here we've got a slight extra complication, remembering that this means the whole thing is squared. So now I've got a function inside a function inside a function. So I've got a double chain rule. We've done this before, but it can still be a little bit clunky. So here's what I propose we do. I'm going to say this is sine of 4x, and even though the whole point of this is to get rid of them, I'm going to say, hey, I'm going to put this on the outside. And then we're going to apply chain rule from that because it's easier to see where our functions are. Okay, well, chain rule is the derivative of the inside. Okay, the derivative of this is all of that rule. So I get 4 multiplied by cos multiplied by its original inside. So this is the derivative of the inside of green, multiplied by the derivative of the outside, being just green, that'd be a 2, multiplied by the original inside. Cool, let's double check that, make sure we're okay. So, derivative of the inside is this section, derivative of the outside is the 2, and then the original inside. Keep in mind, if that was a 3 or something, then this guy would have been squared and this would have been a 3. Cool, beautiful. Now, that's not the neatest form I've ever seen, so let's neaten him up. 2 and a 4, 8, these two, there's a couple of, what do you call them, identities that you could play around with here, but I'm just going to leave it as that, because it's not getting particularly better. Beautiful, done. Okay, well, we've got more fiddliness to go. Product rule here, because I've got a function multiplied by a function, and I've also got chain rules operating at the same time. So, whenever you've got that many things going on at once, usually a good idea. Write out some stuff. Here's my u prime. So here's u, this is going to be u prime. Derivative of the inside, 2, derivative of the outside, cos, original inside. V prime. Cool. Yeah, we'll do it in that colour, doesn't matter. Derivative of the inside, 2x. Derivative of the outside, negative cos. Outside, sorry, original inside. Sorry, that should be a sine. Oh dear. I was too worried about trying to fit that negative in. That's alright. This is a 2x times negative sine, by the way. Cool, okay. F prime, so derivative of the whole thing, u prime, 2 cos of 2x plus 1 multiplied by v, which is cos of x squared minus 1 plus u, which we'll do in blue, because it was part of the original, multiplied by v prime. So we've got 2x multiplied by negative sine of x squared minus 1. Excellent, what a big chunky. Alright, let's see if we can neaten this up. Well, that's not going to go anywhere fast. Notice that this is a cos times a cos, so that you can't just jump these things together. Doesn't work like that. We've got a negative in here, so minus 2x by sine of 2x plus 1 times, sine again, of x squared minus 1. And that's all she wrote. I can't jump these in together at all. There are potentially other versions of the same thing, but they're not going to get particularly better, I don't think. So that's that. Cool. Quotient rule. Same as before, highly recommend. Write out whatever your derivatives are. Derivative of the inside, negative 5 sine of 5x plus pi, v prime. Derivative of the inside, 3 cosine 3x minus pi on 2. Cool. This is now chopped. That's for that guy, this is for this guy now. Cool. U prime. negative 5 sine 5x plus pi. U prime, we need v, which is sine 3x minus pi on 2. Minus u prime u, which is cos 5x plus pi. Purple. V prime. 3 by cosine 3x minus pi on 2. And the party's not over yet. I've still got to go that whole thing over v squared, which I can write like so. Brilliant. Okay, can we neaten this up at all? Well, I've got sines, but there are different arguments. Just the negative 5 here. No, can't do anything with him. Here we've got cos, but different arguments. 3, negative 3, nothing much there. So I could cancel this with this, but then I'm going to end up with 2 separate fractions. So does that really make it any better? Not so much. So particularly on exam 1, on usually question 1 or question 2, usually you are better off leaving it like this, because very commonly people will simplify it and it just goes horribly wrong. So usually you want to leave it like that, unless some of these arguments are exactly the same. Then you can start to do, well, if this was sine 5x plus pi and this was sine x plus pi, then you just go, oh, well, that's, instead of negative 5, negative 10 sine 5x plus pi. And similar story for the rest. Almost always this won't simplify nicely. Every once in a while you get a nice one, but most of the time it'll be some ugly, horrendous thing, as you see here. Cool, so that's that. It's more or less just applying those rules as trig functions appear, and then it's still the same chain product quotient, and then if you're unlucky, then it'll be chains within chains and products within quotients and all the rest of it. But it's very much just set yourself out and chunk it bit by bit. Cool. Email me if you get stuck on any of them. Best of luck.